Hello. So I'm going to be gone this afternoon. So I wanted to make a video, and I think you've seen this stuff before, and this should be kind of a nice, easy chapter after making it through 11 and 12. So let me just go through the basics of it. I'll go through some example problems. So, of course, the whole idea for dynamics, it all comes back to this very cool equation, F equals ma. And for the acceleration, there's two different ways to think of acceleration, right? You can think of acceleration as velocity changing with time, or the other way to think of acceleration is you could use that little trick to get rid of time. Remember that? So the other way to think of acceleration is v dv dx. If you put a time dependency in this, it will turn into impulse momentum. Okay, so this is where you start with some velocity and then you smack it. Usually it's a very short time period, like hitting a baseball or something, and then you end up with some later velocity. So that's if you have a time dependency versus if you have something that's not changing with time, but happening over a distance. So if we slap this into it and pull the x over, this is where potential energy and kinetic energy fall out of it. Or you could think of this as work and energy, but you have some starting velocity, some ending velocity, and if you crank through this integration, what you do is you have some starting energy, and this is velocity squared, so it's not negative or positive, up or down. It's not a vector anymore. This is a scalar property, and I'm going to leave f dx as is for now because this is going to turn into either work or potential energy or a whole bunch of different things. And after this force through a distance happens to the system, down the road, you're going to now have some new velocity happening. So for either of these systems, what you're going to do is it's kind of like a movie that you're going to grab some snapshot. So you're going to look at the starting situation. What are the starting velocities? And then something is going to happen to change that start, okay? And this could be either an impulse, something smacking it real fast through time, or friction through a distance, or maybe a spring force through some deformation, or MGH. There's going to be some kind of a force that happens through a distance, and then at the end of all of that, your system will have a new velocity. It'll have a new kinetic energy, a new momentum, and for this one, I think it's a good idea to draw where it starts, what changes it, and then where does it end? Does it come to rest? Does it start from rest? And energy is kind of an interesting thing. Sometimes the path matters. If it's friction, then the path matters. If it's something like MGH, it doesn't matter what the path was. It could be anything, but just put a giant summation sign. So any force that will change the energy, you'll figure out what the final velocity is. Okay, I'm going to pop over and show you just a couple example problems out of the book. And I'm going to show you those problems solved several different ways. And this is everything in dynamics applies to everything. Like there's no right way to solve it. You can use kinematics, you can use kinetics, you can use work energy, you can use impulse, momentum. All of those equations apply to all scenarios. It's if you're in the realm of classical mechanics and not quantum mechanics or something weird, it all works and it all gives you the exact same answer. Okay, so let's say we have, and this is a chapter 13 problem, But I'm going to walk through the chapter 11 solution, and then I'll walk through the chapter 13 solution, and you can see no matter how you solve it, you get the same answer, and then you can decide which is the easiest route to go. So let's say we have someone who's dropping a rock in a pit, and you want to figure out maybe how high the pit is. This is like, the cat falling at the football stadium, if you know how long it takes, or you can figure out velocities and distances and stuff. Okay, so if we had some kind of information, like maybe we knew the weight of the stone, so 0.5 pounds. Remember, this is weight versus mass. So when you say F equals MA, make sure that's in mass and not weight. So get those units sorted out. And if we're dealing with pounds and feet per second, we're going to be using 32.2 feet per second. Okay, so let's say somehow we know the velocity that it strikes the ground. So we're going to release it from rest. It's going to hit the ground at 95 feet per second. And if we have that information, could we figure out something like, I don't know, the time it takes to hit the ground, or maybe the height? Okay, so let's say that we figure out what the time is, right? So we can go back to our chapter 11 equations that the position of that rock is equal to where it starts. So we can say, let's call the ground 0, and it's actually going to be negative going into that pit. And we'll say that it starts from rest, so we have a starting velocity of 0, and maybe we know that it is falling with some 32.2 feet per second squared. So if we know the final velocity, right, so that final velocity, I guess if it's going down, we better make that negative. So if we get all of those guys in there, what we can do is we can say, how long does it take for it to reach that velocity? And if we know that time, plug that time into our old position and say, how far down under the ground was it when it hit? Okay, so this would be the chapter 11 version of solving that problem. And we could see how deep the pit is, that it's 140 feet deep. Maybe you think back and say, well, this doesn't ask for time, so why are we messing with time? Let's go to that other constant acceleration equation. V squared equals V1 squared plus 2A times the displacement, right? So if we do the same thing, and we can make that 32 negative, or make sure we have this in the right direction, okay? So there's that 140 again. So whether we use time to solve for it, or we say, let's use that other constant acceleration equation, and that makes it a little bit faster. We don't have to solve it for time. Okay, could we do the same thing with an energy balance? So once again, we have the weight of the thing, the mass of the thing, the starting velocity, the ending velocity. We'll give it a starting position of 0. And to solve the same problem using an energy balance, so you would say, what's the starting energy? And maybe we're dropping it from rest. So it starts with a 0 velocity. And we'll say that it's some height above the bottom of that pit, right? So there's some kind of an MDH. This MDH, that is a force through a distance. So if I integrated f dx, that's what I would get, MDH. And I have a plus sign here because this is making the thing go faster. So for work and for potential energy and which way you're going, just ask yourself, is that force through a distance making the velocity go faster, or is it slowing it down? So if that was friction, it was slowing it down, versus it's, falling and the gravity is making it fall faster and faster and faster, but it's not a vector. Pure magnitude. This is a scalar properties that you're worried about the magnitudes. Okay, so then here is the final kinetic energy, and again, we're using mass here, not weight. And if we know the final velocity, there's that 140 again. So it's the same answer over and over and over again, no matter if you use an energy balance or constant acceleration equations. You play these games with math, and it turns out to be kind of the same thing either way. If you don't break any rules in math, it's that's what it is. But you're looking at the starting energy, force through a distance, the ending energy to walk through this thing. Okay, here's another one. I like this one because it has a velocity that now has two different directions. We've got something going on in the x direction, something going on in the y direction. We did projectile motion before, so this was like that PhET simulation, right? That you had a cannon and you shot something with the cannon and hit a target. So hopefully everybody's kind of really good at those projectile motion simulations. So let's say we have a mass and, they give it to us in ounces. So we're going to have to look at what is ounces for pounds and figure out some conversions there. And then here's that weird mass so we're going to take pounds divided by feet per second squared. So it's kind of a strange unit here. But once you get through the units of this, if we have the starting angle, and you can split things into x and y components, can we figure out something like how high does that baseball go? And maybe what's the velocity that it hits the ground with, or something like that, right? So the old way that we would solve this is we would have some equation for what's happening in the x direction. So we'll say no air drag, so no acceleration in the x direction. And in this case, that velocity does not change. If there's no force in the x direction, the velocity in the x direction is constant through the whole system. The y direction, because there's a force in the y direction, there's gravity acting in the y direction. So that means this piece of the velocity is changing. So we're going to have some starting velocity. We can break that vector into horizontal and vertical components, and then it's going to change in the y direction. So to find the maximum height, and you have to think through physically what's happening. At the maximum height, it's the y piece of the velocity that goes to zero. The x piece is still flying. The x velocity still has it's still going forward in the x direction, but at least in the y direction, the y velocity goes to zero before it starts falling down to the ground. So if you can find the time that the y piece of the velocity goes to zero, that will get you the time it takes to get to the top and how high up off the ground it is when that happens. So if we start from 2 feet up, we can plug that 2 feet into our starting y position. We can figure out our starting y velocity. We can plug in our gravity, make sure we have gravity in the right units here. And we can figure out the height, the maximum height that this would reach using those old Chapter 11 kinematic relationships. Okay, how about something like find the velocity it hits the ground with? So again, we can say, well, I know the position of the ground. We're going to say that is at 0. And maybe I want to figure out the x position of how far away. So we'll just call that the length in the x direction that it travels in. And then the velocity it hits the ground with, there's two pieces to that velocity, right? There's the x component and the y component. And if we can crank through all the derivatives and figure out what's happening in both of those directions and add them together, that would be that final velocity. Okay, so you crank through all of the derivatives and plug in numbers, right? And you can figure out, okay, there's the height that it reaches, and then the velocity and the length of where that target would be. And it has squares in it, so there's a whole bunch of different answers. You have to come over here and say, oh yeah, it's traveling to the left. And this would be the magnitude of the velocity it hits the ground with, and the total time of flight, and all that good stuff. So we've done that before in Chapter 11. Is there an easier way? So what if instead of using constant acceleration equations, what if instead we looked at 1/2 mv squared. We looked at the energy balance of this thing. Okay, so here, let's walk through the same scenario. So we will start with 40 degrees and 5.1 ounces. And we'll say that our starting velocity is this 130 feet per second. Now, for the height, energy-wise, so you're thinking mgh, 1/2 mv squared. There's actually two different ways to go about doing this. You can consider what is happening in just the y direction, or if we were looking at the entire energy of the thing, maybe let me redo this, because it's a little bit confusing, because kinetic energy is not a vector. Like, you shouldn't have to split it into x and y components. So if I consider the entire 130 feet per second to start out with, and my mgh1, so remember, this is not starting at the ground level, it's starting at 2 feet up, and I want to take this up to the highest point. So what I would have to do here, if I'm starting with the entire velocity, is I would have to realize that, at that highest point, I still have a kinetic energy up there. I still have the x piece of my velocity up here. So this x chunk of the velocity, it is actually not changing. It goes through the whole thing. So whether I take the entire velocity at the starting height, and then when it comes to the top, so that ball has come up and it's now at its maximum height. That maximum height is where there's only the x velocity is left. The y velocity has gone to 0. Then I can figure out what that height is. For hitting the ground, it's a little bit easier. So I start with my 130 feet per second. I start with mgh. And in this case, I don't have to worry about how high it goes. I'm going to just skip to the end and say at the very end, I don't have an mgh. There's no mgh when it hits the ground. That mgh goes to 0. If you want to, I can say plus 0. So I can get the velocity it hits the ground with. Okay, so here's that guy solved. So whether you just consider what's happening in the y direction, or if you look at the entire energy of the thing, and that's where it kind of gets, you have to really think through that to realize, hey, there's still a velocity in the x direction when it reaches that maximum height up there. So think through what is happening kind of at that first snapshot versus a second snapshot, and 110 versus 130.5. So you can get the exact same. So there's that 130.5, and there's the height of 110 that we got through all of this method. So it's, one way or the other, it doesn't matter how you solve the thing, you're going to get the same answer. And you can decide if it's easier to crank through the energy balance on those things, or I think once you learn one way to do it, it's kind of habit to go back to what you're comfortable with. But there's a lot of problems that these energy balances can be the fastest way to crank through it. Okay, for potential energy when it comes to this GMM over R squared. So remember, for this thing, what it comes down to is force through a distance. And that force could be mgh, it could be kx dx, goes to 1/2 kx squared for a spring. The force could be a friction force, so friction coefficient times a normal force, and how far it gets dragged along. It's a dot product, actually. So if the force is in the y direction, displacement in the y direction. If the force is in the x direction, displacement in the x direction. But you're integrating this force through a distance. And if you look at this for kind of planetary motion, just a quick thing. So for that one, the force is GMM over R squared. And if you go through that force through a distance, so maybe it's your distance is between the center of the planet and where the satellite is or something. in that case, it ends up being negative dmm over r. So your potential energy here is a negative dmm over r when you're going into these systems. And like before, you just have to really watch your units on this thing. Make sure your position vector is going center to center. It's not going from like the surface of the planet to the center of the satellite or something. So everything in meters, not kilometers, not you have to be real careful on those units and get the right number of like 10 to the 11th, 10 to the 23rd, or whatever it is. It's just the hardest piece of this one is kilograms, not grams, not just get all those units to match up and then you'll have it. Okay, let me pull up and just walk through real quick. So there's two parts to this homework, and I wanted to get through the energy balance stuff, this first chunk, and then coming back on Tuesday, we will do the impulse momentum piece of it. So these are the second half of the problems involve this stuff, and the first few problems involve this. So let's just get through these energy balance problems. I'm hoping they won't be too painful. So these are the energy balance problems in your quiz. This, whenever you get something that says time, okay, stop when you get to time, and then we'll do the impulse momentum problems later. So for this, it's stuff that's happening through a distance. So if it says starts from rest, you have some force like friction. Okay, let's just, we can start walking through a few of these guys. So all of these guys that happen through some kind of a distance, it will be a work energy problem. So if we just talk through this, so this is distance. Anything that there's these kind of key words that whenever you see something through a distance, it's going to be some kind of a work energy problem. Okay, so they're giving us the distance that happens, start from rest. Okay, so the starting kinetic energy, for some reason, the book uses really funny symbols for energy. When I see T, I think time or tension or temperature. They use T for kinetic energy, and I'm really sorry about that. But just that's what you're going to see in the textbook and the notes. So it is what it is. Okay, so we'll say this thing starts from rest. So we'll start with a kinetic energy of 0, and we have some kind of a force, friction between the tires. Okay, if this is ice, if there is no friction, the car is not going anywhere. So the motor and all the internal forces aside, when I draw a free body diagram of this, what makes this thing go forward is the friction force. So if this is going to have some kind of an acceleration, okay, mass times acceleration is equal to the force. The direction of the force, that's what creates the acceleration. And this is where the friction actually acts in the same direction as the car. Okay, if there's no friction, the car doesn't move. The tire pushes back on the road, and the road pushes forward on the tire. It's a little bit backwards. Usually you're used to friction as like, oh, the block slides down the hill, and then the friction acts in the opposite direction of the block. For a car, it's backwards. It's because of those rotating tires. So if the car is going forward, the wheels are kind of digging into the ground, and you have an equal and opposite force pushing the car forward. So that the friction force in this case is in the direction of the acceleration. And it's it's a little bit odd sometimes to realize that friction is in the same direction as motion for tire stuff. Okay, so our force through a distance here, that is going to be our friction coefficient. And if it's leaving tread, that means that it's kinetic friction coefficient. Hopefully we're not leaving tread, and it's that little spot of where the tire hits the road if you're not sliding around and actually... Okay, so that's probably not a good situation. We want to have static friction coefficient. What happens is, the tire is rotating backwards as the whole car is going forward. And if you look at actually the velocity profile across the car tire, that velocity profile will look like this. So the whole thing is going forward, but then it's also rotating. Okay, so the rotational motion looks like that. And when you add together the forward motion and the rotational motion, these guys cancel one another out, and you end up with a zero velocity where the tire hits the road. And that's what you want. You don't want your tires sliding around on the road. So that's another kind of crazy thing to think through what's happening here. But it ends up actually being a static friction coefficient. And that's getting into the second half of the dynamics book, to think about why that velocity is zero and why it's static. So we have hopefully a static friction coefficient if it's not slipping. And then if this is a rear wheel drive or front wheel drive, so you're looking at the tire that is actually hooked up to the engine that's driving the car, okay? And so there's going to be different scenarios here, right? Is it sliding? Is it not sliding? So this is leaving treads behind, little pair of 11s, versus static, where it's not sliding. Sliding. Okay, so anyways, my computer is glitching. And then your normal force, is it the back wheels driving it? Is it the front wheels driving it? Is it, all four wheels going? So you can see which piece of the car. And this is where, you might want to put the battery in your trunk to get a little bit more traction back there, because it is the friction that is doing this. Okay, so that is but you're going to have some starting energy, some kind of a FDX. So this force is happening through some distance, right? 125 meters. This is 125 meters. And you want to see what the final velocity is going to be. So you have your starting energy, you're going to have a force through a distance, and that's going to give you your final velocity. So you can see how fast you can get up to in 125 meters if you're like all the way up to the edge of what friction can handle in that scenario. Let's see, for this guy, for springs, it's going to be a slightly different force through a distance. And this is where we have something happening with MGH. We also have a spring being compressed. So it starts to be a good idea to walk through multiple pictures of what is going on. So you have what's happening at the beginning, and then think through all the forces, any force that's going to change the final velocity, and then what the final velocity is. So you're have some starting point. Okay, I'm recording this while it's stormy outside, so it's been a little bit, sorry about that. Okay, so let's start right here. And then we want to figure out the maximum deflection of the spring. So it's actually going to slide down the length, and then it's also going to compress the spring. So the final position is going to be some combination of that. So it's going to be an MGH that happens, where this is going to be a combination of the length, and I'll call this D for deflection of the string. So the H piece of that, if you have a triangle, right? If this is L plus D, then this height is going to be L plus D sine theta. It's going to be a combination of both of those distances for that height, for your MGH. And then we're also going to have, so your force from the spring. So this is going to be 1/2 kx squared, where this little piece is going to be just how much the spring is compressed. So for the starting energy of this thing, so we'll say it maybe starts from rest. And the two things that will change this are both MGH and a 1/2 kx squared. And the final energy that this is coming to is at the very bottom, it will have a kinetic energy of 0. So the velocity has come to 0, and we'll say that our height is a 0 here too. So we'll call ground level the lowest position of that weight. So for any of these energy balance problems, the point is there's a giant summation sign on that FDX. So any force through a distance, whether it's MGH or a spring force, you just keep adding it together, add it together, add it together. Any force that changes the velocity, keep adding it together. If it speeds it up, it's going to be positive. This is making the final energy larger as it falls. If it slows it down, it's going to be negative. So as it compresses the spring, that spring is what stops the thing from falling, right? So as you're writing that equation, you'll have the starting energy, and let's say it starts from rest, and then you have gravity trying to make it go faster. So that's going to be that height that you have to figure out, right? So you have to really think about how far it's falling. And at the very end, then the spring is going to slow it down, and then the final energy of this thing is 0. So this one, the kinetic energy, 1/2 mv squared to 1/2 mv squared, that's not really doing much. So it's just falling versus slowing down. And you can figure out maybe how far that spring is going to compress to make it stop. Or if you want to see the max velocity, you have to ask things like, well, where does the max velocity happen? And the max velocity happens right before the spring starts slowing it down. So some of these, think through physically what is happening and then go from there on these guys. So let's see another spring one. And this is nice. If it was a force balance, then you would have to break the force into X and Y components. That force would be changing as you stretch this around, versus if there's no friction, without friction, then you just grab it at one location, grab it at another location. You're looking at 1/2 kx squared, and it turns into it's a lot easier with an energy balance for this one than trying to figure out forces. Forces would be a nightmare, because the force from the spring is changing all over the place, versus an energy balance. You just grab where it starts, where it ends. You look at the difference between the two, and you're done. Okay, the train. You've seen this train problem before. Remember when we had brakes? So that's kind of an interesting thing. You'll see the same problem over and over and over again, and it's just see if it's, easier to solve it with an energy balance. And a lot of times it is easier. So this is similar to what you had before, where you can look at the entire system and figure out the entire system versus you look at just one car. So when I'm doing my work in energy, I can define this energy as the energy of the entire train together. So it's adding up, if they're all attached to one another, they all have the same starting velocity. So then I can say mass of A plus mass of B plus mass of C. So they're all barreling down the tracks together. And for the force, then you're looking at the force on the entire system together. So whether you have brakes on one or brakes on another, so you would add together all of those brake forces. So add together brake force on A and brake force on B. They all act through the same distance, right? So there's some kind of a distance that it's going to stop through. And then maybe at the very end, the whole thing it stops, it comes to rest, right? And then you can say, oh, what distance did it stop over? Instead of looking at the entire system, I can tear this thing apart and maybe just look at train A. So if I'm just looking at train A, then I would start with just the kinetic energy of train A. And then I would look at just the forces on train A. And in this case, it might be a brake force. And then it would also be the force in between A and B. So whatever crosses the boundary, I have to keep track of any force that crosses the boundary. So now I would have this little link between the trains is now acting through that distance to bring the A train to rest. So for however you dice this thing up, sometimes it's easier to just kind of group everything together, in which case internal forces go away and you're only looking at, the braking force versus just look at one train and just look at the forces acting on one train through some distance. And you can play these games where you carve it up different ways to get through this thing. Okay, so I think we talked a bit about this. We didn't do the conservation of angular momentum, but potential energy for these guys is negative GMM over R squared, and that comes from integrating force dx. GMM over R squared dx turns into this negative GMM over R. So anyways, if you can get through those first few problems, so when you get into these impulse force through a time, stop, and we'll do those problems starting on Tuesday, but then for the rest of them, see if you can get through these initial problems, and hopefully you'll enjoy the energy balance way of solving these problems. And it seems like a little bit of repetition to go through these things. It's the same train problem again, but now you're solving it with an energy balance instead of with forces. And you get the same answer either way, but it's a game of what's easiest, and energy is often the easiest way. Okay, hopefully that'll get you started. I will be around. Text me if you want to go through any of this stuff. And sorry to miss class tonight, but hopefully that's all you need for this, and you can watch this in fast forward mode and get through it quicker and enjoy the weekend, this great fall weather. And we will see you on Tuesday.